Okay, let's get started. This is another topic that is pretty high importance to analytical chemists, as it turns out. It's one of so-called figure of merit of the analytical methods that you might deal with. And this is an oft-quoted one, as it turns out, and it's a pretty high importance to know what this is about and why it's important. So I'm going to rate it 3 out of 4 stars. You may or may not see a question on a standardized exam exactly related to this. However, the discussion is of high relevance to professional analytical chemists. So you need to know this stuff, all right? So the topic is limits of detection and limits of quantitation. And basically what this is all about is establishing quantitative metrics of performance of a technique. Okay, so if I was to ask you basically just kind of at a back of an envelope type of way to compare these two figures, and basically what this is just a plot of some signal that's produced by a detector. Maybe it's an electrochemical detector or whatever, it doesn't really matter, and that signal is plotted in time. There's 2 experiments, one here and one here. These are done at we'll say different concentrations. Okay. And my question is it convincing that this little blip on the diagram is a true signal, or is it more convincing that the one over here is a true signal? Okay, you have to apologize. My artwork is not beautiful here, but what I'm aiming to show you is that this peak is much more bigger than this peak over here. Okay, and not only is that peak bigger, it's much larger compared to the random fluctuations or the noise in the baseline. Whereas over here, the random fluctuations are a reasonably high percent of what I've drawn here. So I would argue it's much more convincing that the signal on the right is a true signal. It's actually been detected by this detector that we've been using. Compared to the one over here, I mean, this little blip, it might be a signal. Maybe it's a signal caused by an analyte response, although it might just be electrical noise in the baseline. We don't really know. So this then begs a question. While this figure on the right might seem more convincing to us visually, is there a way that we could establish a quantitative measure of whether a signal is detectable or not? And of course there is, and that's the topic of the remainder of this video. How do analytical chemists establish limits of detection and limits of quantitation? Those are our key terms. They are abbreviated L.O.D for limit of detection and L.O.Q for limit of quantitation. So what do these things mean? How do we define them? Okay, that's the topic essentially of this video. I'm going to start off just by kind of giving you some quantitative bases for establishing these things. Okay, the 2 equations down here at the bottom of the slide are essentially the mathematical statements that you'll want to keep in mind or remember. Okay? These 2 equations are related but not exactly the same. The reason why this is because on the left I've written an equation for what I like to call the signal domain, and on the right I've written an equation for the concentration domain. Okay? There's different domains of information in analytical chemistry, just kind of like what I've shown up here. These plots are in the signal domain, and basically what that means is you plug in a detector to the electrical outlet and you use it to make a measurement, and it produces some sort of electrical signal in time. And hopefully, if your detector is working right, the detector signal, the magnitude of it, the size of it, is somehow proportional to the analyte concentration. So in this case, we alluded to the fact that we get a bigger peak or bigger detectable signal for a detection event, a chemical detection event. So presumably this would be at a higher concentration than the one over here on the left. But nonetheless, the information that we get out of this, that at the peak height or area, is a detector signal, and it has some root in electrical current or voltage or some sort of electrical measurement. So it's the signal domain. If I want, I can define a minimal detectable electrical signal in the signal domain as being equal to the electrical signal for a reagent blank This, of course, is essentially the matrix with no analyte, basically. Okay, so it's a sample that contains no analyte, or zero concentration of analyte, or as close to zero as we can get. The signal that is produced at the detector, it might be non-zero, so there might need to be a non-zero number that goes there. We're going to add to that 3s. What is 3s? 3 times s. Well, s, simply stated, is the standard deviation of replicate analysis of a sample of concentration that is near the detection limit. So it's essentially a measurement of the imprecision for replicate analysis of a sample which is analyzed several times. The sample has to have a concentration of analyte near the detection limit. So sometimes it'll be a little higher, sometimes a little bit lower. I can get a distribution of data, compute the standard deviation for the replicate analysis, 3 times that. That's what goes right there, okay? Now, a couple notes about this S and the computation of S, okay? We want the sample to have a concentration near the detection limit, so we're going to analyze the same sample over and over and over again to get the standard deviation. That sample should have a concentration of analyte in it that's near the detection limit. Hopefully anywhere between the detection limit and maybe 5 times the limit of detection. Okay, so in that range is the approximate concentration that we want. In addition, to get a good measurement of S for use in these equations, you really like to have at least 5 and maybe even 7, 8, 9, 10 replicate analysis. So the S that you use is a pretty good estimate of reality. Okay, so you want to have multiple analysis, not just say 2. That would be kind of silly to compute S from that. Okay, so nonetheless, it's some experimental details about finding S for use in these equations. But if I know what S is, I can multiply it by 3 and add it to the signal from my blank. That gives me my minimal detectable signal. Okay? Notice here that the standard deviation should also be in units of the signal, so it's also in the signal domain. So all this is in the signal domain, and I get a minimum detectable signal. Now, another thing about this before we go on, I multiplied it by 3 over here. Why in the world multiply it by 3? Is there some kind of rationale for that? In fact, there is. If you've watched the videos on the Gaussian distribution, which you should have done by now, the normal distribution, you'd find, or you'd learn in those videos, that the numbers of standard deviations away from the mean matters in terms of the probability with which a given number will belong to a certain set of data or a certain distribution of data. The further away from the mean we go, the less likely it is a number belongs to that distribution of data. And in fact, if you go 3 standard deviations away from the mean of a data set, if it's normally distributed, which here we assume it is, if you're 3s away, only a handful, about 3 points out of 1,000, are outside of that range. So if we are in fact 3s away from the signal for the blank, which is kind of like our average of our distribution, if we're that far away, only 3 out of 1,000 times will we get there by accident or by random chance. So this 3s standard that we're going to use for detectability, it's also going to show up over here when we talk about that stuff. It's rooted in the Gaussian distribution. If you're that far away from the mean, it's very unlikely that you did that on accident. Okay? So there's really a rationale for that. It's really not just randomly chosen. If you're that far away from the mean, you're pretty sure that what you've detected is a true detectable signal. So that's the signal domain, minimum detectable signal. That's an electrical signal. However, usually chemists worry about minimal detectable concentrations because we're dealing with the concentrations of analytes. So while this is important to us, and it's certainly related to minimum detectable concentration, we'd also like a way to compute the minimum detectable concentration that we can detect. We're able to do that by using this equation, which you should commit to memory. 3s divided by m is our minimum detectable concentration. Again, s is the same as it was previously. The standard deviation of replicate analysis of a sample of a concentration near the detection limit. You need to figure that out experimentally by replicate analysis of such a sample. But here I'm going to divide by another number, m. m is the slope of a calibration curve. for standards of higher concentration, higher than the detection limit. We also call that the analytical sensitivity. It's the slope of a calibration curve. If I do 3s divided by m, that's my minimum detectable concentration. I can also define lower limits of quantitation, which are sometimes called L.O.Q, or often called L.O.Q. The lower limit of quantitation is the smallest amount of analyte that can be measured with reasonable accuracy and precision. Now this isn't necessarily, when we say measured, we're not talking about the same thing as L.O.D. These equations were for detecting the signal or detecting the analyte. And when I use that word detecting, what I essentially mean by it is whether or not we can confirm the analyte is present in the sample. We have detected its presence. If the signal is bigger than 3s plus this, we have a minimum detectable signal caused by the analyte, and we have detected the analyte's presence. But what I mean by L.O.Q is something a little bit different. In the case of L.O.Q, we're actually trying to quantify the analyte. We're trying to write down its concentration on a piece of paper. You know, it's 25 micromolar or whatever the concentration is. We're quantifying and reporting the concentration of the analyte in our sample. That's different than just detecting it. This is actually reporting the concentration. So when we say lower limit of quantitation, what we really mean by that is the lowest number or concentration that we should report to, say, our boss or in a journal article or whatever it is that you're working on. Turns out that a higher standard is used for quantitation. We use the standard 10s. So 3s is transformed to 10s here. But the equation that we use is essentially very similar to the one for L.O.D, the detection limit, except now we use the 10 times the standard deviation standard divided by m instead of the 3s divided by m. So L.O.D is 3s divided by m, L.O.Q is 10s. It's a higher standard. S and m are the same as they were before. Okay? So that then begs the question, well, what if a signal that I observe on my detector is somewhere between 3 standard deviations of the replicate noise and 10? What if it's between these two? What if it's between the L.O.D and the L.O.Q? Well, if that's the case, can we say the analyte has been reliably detected? And I would argue yes. I'll put a little check mark. And that's a yes, okay? It's hard to read, but yes. If your signal is between the two, your analyte has in fact been detected within the sample. You can say yes, no fashion, it's present. Analyte is present. Have I achieved the quantitation limit, however? Well, if I'm between 3 and 10, that means I'm less than 10. So I have not achieved the quantitation limit, which means that the analyte has been detected, its presence has been detected, but it's at such a low concentration that I cannot reliably state or state the concentration of or quantify the analyte's concentration with the results that I've got. Okay? Now alternatively, what if a signal that you observe is greater than 10s? Has that exceeded the L.O.D? Of course. So that's bigger than the 3s standard. Have I exceeded my L.O.Q if my signal is greater than 10s? The answer is yes again. So this is best case scenario when I'm greater than 10s. Both of the answers are yes. I've detected my analyte And can I quantify it and write down its concentration, report it on a piece of paper? Yes. Okay? Now what if a signal is less than 3 sigma, or standard deviations? So the signal that I observe is less than 3. Have I detected my analyte? No. Can I reliably quantify it? Not a chance. Not detected it, cannot quantify it if I'm less than 3s. Okay? Now, another hypothetical question. If I run my chemical assay or my chemical test, my method, and I find that the signal produces less than 3 standard deviations of the replicate noise for the sample near the detection limit, I have not detected analyte. Does that mean that 0 analyte is present in that sample? Alright? Does that mean 0 analyte is present? The answer is no. In fact, you might have some analyte present in the sample. The only problem is it's below your detection limit, so you cannot detect it with the method that you are using. If you change methods, use a different method that's more sensitive, has a lower detection limit, maybe you'll be able to detect the presence of the analyte. Maybe you'll be able to even quantify it. But with the method you're using, if you're below the 3S standard, you've not detected it, you can't quantify. It's just below your detection limit. The analyte concentration is below your detection limit. There may be analyte present, you just don't know. You can't detect it with the confines of the method that you've got. Okay, so this is sort of what we mean by it, and some of these logical arguments that are sometimes built into problems, you see that from time to time. So I wanted to take a second to run through that with you so you understand what we're talking about with L.O.D and L.O.Q, and what are some of the logical statements behind this, because they do in fact come up on test problems. Now one more bit of vocabulary before we move on with the sample problem. Something called a reporting limit is related to this discussion. A reporting limit is an amount or concentration below which analyte can be reported as not detected. So you might be confused with the terminology reporting limit as it relates to detection limit or quantitation limit. The quantitation limit is defined by this type of equation. The detection limit is defined by the quantitative equations that we learned about earlier. Those are figures of method. You often sometimes see them reported in product literature for the methods. However, this reporting limit is usually used in different circles, and that's one of the biggest differences. The reporting limit usually is set by some sort of state or federal regulatory agencies that oversee product safety or something of the sort. So you might see it with respect to foods or pet foods or some other safety related aspects of products that we use in our everyday life. So it's usually set by, again, federal or state agencies. So it's the amount or concentration below which the analyte can be reported as not detected. So this becomes kind of like legally important for products that are sold in the marketplace. Because, say for instance, if you have you're quantifying fat in food, you're able to say it's not detected if it's below a certain level. So whatever the state or the federal government sets that level at, if your product's below that, you can basically report it as not detected, almost like there's none present, when in fact maybe some of the fat is present. Okay, so it's kind of a legal thing, a legalese thing, not necessarily completely quantitative or completely scientific. Okay, so understand what this reporting limit is in fact all about. Alright, well while we're on this topic, I did want to work through a sample problem with you. This type of thing might come up in homework, and because of that, it is very useful. Spend a few minutes working through a sample problem to see what you might face. Okay. So this problem reads as following: an amperometric detector is used to record replicate measurements on a sample known to be close to the limit of detection. The signal is obtained for 1, 2, 3, 4, 5, 6, 7 trials. N equals 7 trials, so that's a fair amount of trials. That's good. These are the signals that we see, sort of a low nanoampere range. This is nanoampere, the unit. Seems to hover around 6 or 7. Then we ran an experiment on the same detector for a blank. The blank gave signals a little bit lower in nanoamps compared to the sample. And that's a good thing, right? Because we had hoped that the sample would produce some signal in excess of the blank. However, the blank does not produce a perfectly zero signal. It looks like there's a little bit of an offset that we might have to talk about here in a few minutes. But nonetheless, we've got replicate blank data, we've got replicate signal data. The problem then goes on to read a calibration line, has the equation y equals 0.319x plus 1.24. When the nanoamp signal was plotted against the concentration of standard being in micromolar units for higher concentration. So basically all that's telling me is I went and did a calibration experiment, and I did several different concentrations of standards, and when I put a best fit line, when I plotted nanoamps current, the signal versus concentration, that best fit line yielded that. So the equation's 0.319x plus 1.24. This would be for an external calibration, okay? That'll become important here in a little bit. Now, as I'm starting to read this problem, again, you might be overwhelmed with details and confused, but you need not be. Again, it's just a matter of practice to kind of weed through all the information they're giving you here and understand why each point is important. They tell us an amperometric detector. It doesn't really matter what kind of detector. If you're detecting the limit of detection, which is what we're doing here, it doesn't really matter what type of detector you use. You really need to kind of quickly parse out the data and the blank measurements here and here. We're going to need those in a few minutes once we work the math. And I key in on this data right here, this equation of the line, because I see I have a non-zero offset, which might be important, but the real important number to me, this is 0.319, because that is my m, the slope of my calibration line. I'm going to need that when I'm computing limits of detection. So of course our hope here is to compute our limit of detection and also our limit of quantitation based on the data that we're given. I think we'll be able to go through and do that. Now the first step in this process is if you're given raw data like we're given here, you always need to compute the mean and the standard deviations for both distributions, the blank and the signals for the sample near the limit of detection. Okay, so we've got to start out with the means and the standard deviations for both of those. And at the time, I've already tried to go through and do this. The blank average was about 1.24 nanoamps signal, and the standard deviation worked out to be 0.276. The average for the sample was 6.45. Include a 7 there, and then standard deviation was 0.934. And that's nanoamps. They all carry that nanoamp unit. So if I was to ask you, are we in the concentration or the signal domain here? I hope all of you would see that we're in the signal domain, right? Because we've got nanoamp units. This is an electrical signal. Hopefully it's proportional to concentration. But it's not necessarily in concentration units, so it is in the signal domain. Okay, so we have completed our first step along the way here. We've got the means and the standard deviations of our data set. The next thing I'd like to work with you is the computation of the signal limit of detection. Signal limit of detection. Remember back from our first slide, we talked about the minimum detectable signal being equal to the signal for the blank plus 3s. That's the equation that we're going to use. So now we just need to figure out what numbers to use. Well, from our data set, remember we computed the average of the blank signals We said that it was 1.24 nanoamps. That's going to be my blank signal. When we computed the standard deviation of the samples of replicate analysis of the sample near the limit of detection. That's really a mouthful, but all the words there are important, okay? The replicate analysis of the sample near the limit of detection. We previously saw that the S for that was the 0.934 nanoamps. That was for the data set of the actual sample, okay? The actual sample that we analyzed that was near the detection limit. That was my S. So if I multiply that by 3 to get my 3S, I end up with 2.8 or so nanoamps. So to generate my answer then, I've got to add these two numbers together. I'll break out my calculator and do that real fast. I find that my signal L.O.D was 4.04 nanoamps. If the signal is bigger than that, it's been reliably detected based on the 3 sigma standard. If it's lower than that, the signal has not been reliably detected. Notice that what I did is I added my 3S standard to my blank offset. This was not 0, so 0 analyte did not produce 0 detector signal, so I had to do this addition to find out the absolute magnitude of the minimum detectable signal. And what's that? Okay. So I'm done with my minimal detectable signal. Now I'd like to compute my minimum detectable concentration for this experiment. If I look back to my standard for definitions purposes, we find the minimum detectable concentration, or the limit of detection, 3S divided by M. It's a very standard equation that you'll want to keep in mind, okay? Commit to memory. Now again, what are the S's and the M's here? The S is the standard deviation for the replicate analysis of a sample known to be close to the detection limit. In our data set, that's this data. The signals obtained for the sample close to the limit of detection. Look at this language, okay? You'll see that a lot when you're looking at these problems. Sample known to be close to the limit of detection. That's basically telling you that that data set is what's important for establishing your S. So I took the standard deviation of that data set, or the replicate analysis of the sample near the limit of detection. And that standard deviation is essentially the same as the S that we used up here, which was the 0.934. So now I multiply that by 3. The equation tells me to divide by M. Now, what in the world would be my M? Well, if you remember from the equation, I said that was the slope of the calibration line, or the analytical sensitivity. So remember back in the problem, we were told in this last point a calibration line has this equation. Well, guess what? That's my slope. That's my analytical sensitivity, this 0.319. So that's the number. It's going to ultimately go down here. 0.319. Now, as I'm doing this, I'm being a little bit careless, I feel, because I'm not keeping track of units as much as I'd like. Okay, so let's go back and look at the units real fast, because that's important for this. This 0.934 was the standard deviation of the replicates. It's in nanoamps. Okay, so the units in my numerator will carry that in nanoamps, because this is just a constant of 3. Okay. Now, what about my denominator? Remember, that was the slope of the calibration line, the 0.319. Well, what units would that slope carry? Well, slope is what? Delta y over delta x for such a line. So it's going to carry the y units divided by the x units. Now what are those? Okay, well, it looks like this equation is for a calibration curve when nanoamps signal, okay, so nanoamps are here, was plotted against the concentration of the standard. But what were the units? It was micromolar. Micromolar. So nanoamps per micromolar are the appropriate units to carry here. Now, why in the world is this important? Okay? Well, the reason why is because this nanoamps cancels out this one, and the only thing I'm going to be left with once I complete the math is 1 over micromolar, which basically the inverse of an inverse, that's going to be micromolar units. So you see when I'm calculating my minimum detectable concentration, the units should work out to yield a concentration unit, and here it does. So if I do the math on this to find my limit of detection, based on my calculator work here, looks like that limit of detection works out to be right about 8.78 micromolar. So if the concentration is above that, I can reliably detect it. If it's below that, I cannot reliably detect it. Okay, so that's my minimum detectable concentration. Now what if I wanted to get really fancy and calculate my limit of quantitation? Could I do that? Sure, that's no problem. Because the formula just told me to use the 10S standard instead of the 3S standard. So everything is more or less the same. The S is the same. The units are the same. M is also the same. And the same cancellation occurs. I'm still going to get micromolar over here. The number that I use for M, of course, is the same. That's the slope of the external calibration line. Units cancel, and I end up getting about 29.3 micromolar for my limit of quantitation. So, if my sample has an analyte concentration above this, I can write it down on a piece of paper and report it to my boss, or report it to whoever I'm writing my report to. However, if the concentration is below this limit of quantitation, I should not really state the concentration because I don't know it precisely enough to write it down on a piece of paper. So these computations come up from time to time, and it's really important that you know how to do this kind of stuff. Again, you may not see it on your standardized exam. However, it does come up in analytical chemistry a lot. So things to remember, if I'm going to summarize, L.O.Q is 10S divided by M. It gives you a concentration. These logical argument types of things, you really need to have a good vision for that. It's easy to ask some questions on this. You know, can you detect the analyte? Can you quantitate the analyte? Is the analyte definitely present or not present? Those logical arguments that we work through is important. We also want to remember these formulas for minimum detectable signal in the signal domain, minimum detectable concentration in the concentration domain. That's also important. Know what the variables are. M is again the slope of the calibration curve. S, it's a word or a mouthful to really state what this is, but remember again, it's the standard deviation for replicate analysis of a sample which contains the analyte that has a concentration near the detection limit. Okay, that's really what that S is supposed to be. And with that said, I think that about summarizes the key points for limits of detection and quantitation. I hope you've enjoyed this video tutorial, and we will see you next time.